Okay, so in this video we will start solving a problem that involves a system of particles, and our goal is going to be through this problem to clarify some ideas of linear and angular impulse momentum relations, how these relations are formulated and used to solve problems. This particular problem will involve particles, system of particles. However, these particles are placed at different locations, and so there is this idea, very nice interaction, or there is a very nice interplay between linear impulse momentum relation and angular impulse momentum relations. So that is what we are going to explore in this problem. So the problem goes as follows. So there are two particles, and these particles are connected by a string. This is a massless string, and it is also not a flexible string, so the length of this string cannot change. So this is M1 and this mass is M2, and they are just lying still on a frictionless horizontal surface, and at an instant there is an impulse which is of the magnitude of M2 V0. That impulse acts on the particle M2, and it causes this system of particles to start motion. And so what is asked for in this problem is the following. So we want to know, first of all, the resulting motion of the system, and number two is the tension in the string, and the tension in the string. So there are various ways to solve this problem, and we will explore the solution of this problem from multiple directions, multiple avenues, multiple approaches. One approach is to consider is to deduce the motion of the center of mass of this system as a result of this impulse. Okay, and once we have deduced the motion of the center of mass of the system, then we can figure out from that how the individual masses are moving. So that is one approach. Another approach is to solve for or to determine the individual velocities or the individual motions, let's say, of the two masses separately as a result of this impulse, and then from there process and find out what is the motion of the center of mass, and so on and so forth. Now let us first look at the motion of this system from the perspective of linear impulse momentum equations. So first we look at this motion from a linear impulse momentum equation of system. Right, so here when we say system, what we mean is for a system of particles, the linear impulse momentum relation basically says that the net impulse on a system of particles is equal to the change in linear momentum of that system of particles. The change in linear momentum of the center of mass of that system of particles. So the net impulse on a system of particles is equal to the change in the linear momentum of the center of mass of that system of particles. By the way, it is also given that the length of this string is L and the string is inextensible. So just to clarify, string is inextensible. So the length always remains L. So now first what we'll do is we will determine the location of the center of mass. So to find this location, we can measure distances, let's say from M2 towards M1. By the way, it is also given that this impulse acts on M2 at a 90-degree angle. So the impulse is 90-degree angle to the string, and initially the two masses are resting at a distance L from each other. So the string is just ever so slightly it is completely it completely has its it is taking the entire length. The distance between M1 and M2 is at the length of the string, and the distance or the direction of the string is perpendicular to the direction at which this impulse is given. So first we want to determine the location of the center of mass. Now let's say that the center of mass is somewhere here. We do not know the exact location, but let's say it is at a distance of d from M2. Then we can say that M1 plus M2 times d is equal to 0 times M2 plus L times M1. Or in other words, d is equal to M1 divided by M1 plus M2 times L. Okay, so we have the location of the center of mass C. Now, to apply the linear impulse momentum equation, we note that the impulse is acting in, let's say this is our x direction and this is y. The impulse is acting in the x direction. So therefore, M2 V0, this is the impulse, in the I direction is equal to M1 plus M2 into VCM, also in the I direction, minus 0 in the I direction. So this is essentially saying that the impulse, this by the way is F hat, which is the impulse, is causing a change in the momentum of the center of mass. Obviously, an impulse, if it is in the I direction, it cannot cause a change in the impulse or change in the momentum in the j direction or in the y direction. Therefore, this equation, this impulse can only change the velocity of the center of mass in the x direction. And so from here we see that the velocity of the center of mass is equal to m2 divided by m1 plus m2 times v naught. So what this means is that at the instant when the impulse acts on this system, at that instant the center of mass starts traveling in this direction, in the I direction, with a velocity vcm. Okay, so the center of mass is starting to travel, so it doesn't matter how these individual masses move. There can be translation, there can be rotation about the center of mass of these individual masses, but whatever happens, the center of mass will keep moving in the x direction with that constant velocity of m2 divided by m1 plus m2 times v naught. Why is it going to be constant? Well, it is going to be constant because this right hand side is actually a constant number. This is a instantaneous impulse that has been given of a definite magnitude, and so it's going to produce a definite fixed velocity of the center of mass, and that velocity of the center of mass will remain unchanged for the rest of the motion. Alright, so so that is one aspect. Now we note that so next we will get to the question of angular impulse momentum equation. So next we will go to angular impulse momentum equation of system. So here the idea is the following, that there is an angular impulse that is produced by f hat, and that is because this f hat is not acting at the center of mass, but it is rather offset from the center of mass. And because of that, when we have a system of particles, this f hat is going to produce an angular impulse because of the fact that it is offset from the center of mass. In other words, it is going to start producing a rotational effect on the two masses. Okay. Now if we consider the motion of the masses, if we try to picture the motion of the masses in our head, this is what the motion of the masses will look like. So here are the two masses, m1, m2, and the impulse, there is an impulse that is provided. The center of mass C is here, right? And we have said that it is going to move with a velocity vcm, which will remain unchanged. And it is also unchanged because after this impulse acts on this system, there is no other force acting on this system. So the velocity will remain unchanged. For that matter, the angular impulse due to f hat will produce a rotation, and that rotational speed will also be a constant speed that will remain forever. So in fact, what's going to happen is if you take an instance, or if you take considered the configuration of the system after, let's say, a second or a few seconds, this is what we are going to notice. We are going to notice that the two particles are now somewhat like this. So here you have M1 and here you have M2. Still the distance between the two is L. The distance of the center of mass to M2 was D, and that distance is going to, of course, remain, because clearly it's not that the masses are changing. If the center of mass has moved to this point, still the center of mass is going to have, the center of mass will, keep in mind that we have said the center of mass will move in this horizontal direction. If this is the x direction or the horizontal direction, the center of mass will keep moving in the horizontal direction with a velocity vcm. So the center of mass is still going to be here. However, because of the fact that there is a angular impulse, so it is going to produce a vcm, and on top of that the angular impulse is going to produce an angular velocity. So while the so now if we consider the motion of these masses to be a combination of that is produced by the linear impulse and that which is produced by the angular impulse, then we can look at the motion like this. The linear impulse produces center of mass velocity of vcm, which is constant for the rest of the motion. The effect of that on the individual masses is that both the individual masses have that same velocity. It is a translational component. It is a mathematical way of looking and separating out the overall motion into two categories. One is the translational and the other is the rotational. The translational part essentially means that we can consider that both the masses are moving forward with that same velocity vcm. Okay. However, on top of that, there is an angular velocity that is created by the fact that f hat produces an angular momentum, and this angular velocity will produce a velocity here. Angular velocities are going to be perpendicular, okay, to the line joining the center of rotation to the point or the location of the particle. So here there is going to be a velocity of omega times d, where omega is the angular velocity, and here this particle will have a velocity of omega times L minus d, and this velocity is perpendicular to the string, and so is this velocity. So the resultant motion of the particle M2 will be like this. That's going to be the resultant velocity. So this is going to be V2, okay, at an instant after the impulse has applied. Similarly, M1 is going to have a resultant velocity like this, V1. Okay, so you can see that the overall motion of the two particles can be considered, for the sake of analysis, as a superimposition of the motion that is produced by the linear impulse momentum and the motion which is produced by the rotational or the angular impulse momentum. The linear impulse momentum equation basically provides a uniform velocity or the same velocity to all the particles in the system, whereas the angular impulse momentum equation causes a rotation of the overall system about its center of mass. Okay, so now our goal is to write the angular impulse momentum equation of this system. And the angular impulse momentum equation of the system is going to be f hat. Now keep in mind that we are going to be writing this equation at the instant when the f hat or rather the impulse acts on this particle. So at that point f hat is at a perpendicular distance of d. So f hat times d and this is going to be f hat times d, and this is going to be an impulse in the z direction, so it's going to be in k. Okay, remember that we are saying that the unit vector I is in the direction of x, unit vector j is in the direction of y, and unit vector k is in the direction of z. So hence we have f hat dk as the angular impulse that is produced by this impulsive force about the center of mass. Now before we write the overall angular impulse momentum equation, we need to just conceptually clarify what this angular impulse momentum equation is. The angular impulse momentum relation states that the angular impulse of all external impulses acting on a system of particles about its center of mass is equal to the change in the angular momentum of all the particles about the center of mass. So this is one statement of the angular impulse momentum equation, and this statement considers the angular impulse and the angular momenta produced all about the center of mass. Alternately, we can write the same equation but about a fixed point, essentially saying that the angular impulse due to all external impulses on a system of particles about a fixed point O, let's say, is equal to the sum of the angular momenta or sum of the change in angular momenta for all the particles about that point O. So this relation holds for only two types of points. One is when the point is a fixed point, or when the point is the center of mass of the system. Here we are working with the center of mass of the system because in this case we do not want to complicate the problem by adding a fixed point at an arbitrary location. So our angular impulse momentum equation of the system is being written about center of mass. Alright, so this is equal to now if we look at the velocities that will be produced in this system at the instant let me just hold on, let me just do one quick thing here. Yeah, so at the initial instant, when these two particles have not yet turned, but it's still in this original configuration or original direction, and the impulse has just applied, at that instance the VCM is still going to be like this. Right, and on top of that there is going to be a omega d in the bottom, and omega L minus d on M1. Okay, and these velocities are all going to be perpendicular to the string. All right, so this is showing the velocities at the instant when the impulse is applied. So you can see that the angular momentum of M2 is going to be M2 VCM plus omega times d. We do not know what omega is. Our goal is to find it out. And the distance is d. Okay, and this is in the k direction, right, and both of them are going in the positive direction, so it's producing a turning effect in the k direction. For M1, omega L minus d is producing a turning effect in the positive k direction, so M2 omega L minus d times L minus d is in the positive k direction, but VCM, which is going in the positive x direction, now is producing a turning effect in the negative k direction, so minus M2 VCM L minus d k. So this is the net angular impulse momentum equation that can be written for this system of particles right at the instant when the impulse is applied. Now, just for the sake of clarity, I'm going to draw this figure once more, a little bit enlarged. So basically what we are saying is that if this is M1 and this is M2, and F hat acts here perpendicular to the direction of the string, and this is our center of mass, then at this instance when the impulse applies, M2 is going to have VCM due to the linear impulse momentum interaction. Due to the rotational impulse momentum interaction, it's going to have another velocity omega times d. M1 on the other hand will have again the same VCM, and that VCM is the same as the center of mass's velocity. That's the linear part, and the angular part is going to produce a velocity omega L minus d, okay, where this distance is d and the overall length is L, and it is based on these, and these velocities are perpendicular to the direction of the string, and it is based on this that we have this equation. Now, since in both sides of this equation you just have components in the k direction, I can simply say and substitute for f hat. So I'll put M2 V naught d is equal to M2 VCM d. By the way, this should be M1. I forgot to put m1. So this second and third expression in the previous page, they are giving the change in the angular momentum in m2 and m1. And by the way, I should also put -0 in the k direction, because that represents the initial angular momentum of both m1 and m2 before the impulse is applied. So just for clarity, so I'm going to have m1 VCM L minus d plus we are going to have m2 times omega d omega d square rather, and plus m1 times omega L minus d whole squared. So that's going to be our equation. Now in principle, the linear impulse momentum equation produced a velocity of the center of mass with which the entire system moves. So it is representative of a velocity with which the entire system moves. So all the individual particles of that system of particles can be considered to be moving with that same velocity. So you can consider the linear impulse momentum equation to give you a fixed constant velocity with which the entire system will move, and on top of that there is rotation. So the linear impulse momentum equation extracts out that that constant velocity with which the whole system moves, okay, if you just remove the rotations from the overall motion. Okay, so by definition, this the velocity of the center of mass velocity that the linear impulse momentum equation gives us is a velocity which is a mass averaged, distance averaged velocity, and so it's a velocity. It's a velocity that is averaged in such a way where there is no rotational effect. So what we expect is that the angular momentum that we get from the center of mass velocities, that is from the linear impulse momentum equations, these two terms should cancel out, okay, and the angular impulse momentum equation should only capture the rotational effect. So we will verify that. So consider the terms m2 VCM d minus m1 VCM L minus d. If we consider this term, then we have m2. Now VCM is as given here, m2 divided by m1 plus m2. Well, there is a VCM that is there in all the terms, so let me just, I don't need to substitute this here. I have m2d minus m1 L minus d times VCM, okay, and so d is we have obtained from our prior calculations, d is m1 divided by m1 plus m2l. So let's make that substitution. Okay, minus m1, and L minus d is going to be L minus m1L divided by m1 plus m2. This whole thing gets multiplied by VCM, right? So we have m1 m2 divided by m1 plus m2 L minus, see, if I simplify this, what I'll get is m1 plus m2 minus m1 times L, so I'll get m2 times L, so I'll get, oh, I'm sorry, this should be m1 m2, not m1 plus m2, so this is m1 m2, and here also I will get m1 m2 L divided by m1 plus m2 times VCM. So these two cancel and it turns out to be 0. So what this is telling us is that the center of mass velocity does not include any angular momentum. It is such a velocity of a system of particles which does not consider any rotation, which does not have any rotation information in it. So the entire rotation information which is supposed to be incorporated in the angular impulse momentum equation is captured within this rotational part. Now you may say that why did I write this? Well, I wrote this for the sake of completion, because by definition angular momentum is r cross mv, and when we say mv, that velocity is strictly speaking the total velocity. So that's why in one case it was VCM plus omega d, in the other case it was VCM minus omega L minus t, and that's why I considered both, and I deliberately put this just to show that this VCM part does not contribute to any angular momentum. Okay, you could say does not include, or you could also say does not contribute. So now we are left with mv0 d is equal to m2 omega d squared plus m1 omega L minus d squared. Okay, so we can make substitutions. We have m2 and d is we already know the expression for d. It is m1 L divided by m1 plus m2, so m1 square L square divided by m1 plus m2 square plus m1 times, now L minus d was m2L divided by m1 plus m2, so m2 square L square divided by m1 plus m2 square, this times omega. Here on the left hand side you have m2 v0. So again, simplifying, what we get is we get omega times L square divided by m1 plus m2 whole squared times so here we have m2 m1 square, and here we have m1 m2 squared, so we have m1 m2 times m1 plus m2. So this cancels one of the m1 plus m2s in the denominator, and we can do a further simplification where we cancel m2 from both sides. So we will have v0 d is equal to omega L squared m1 divided by m1 plus m2 Now we have d is equal to m1l over m1 plus m2, so v naught m1l over m1 plus m2. This is the expression for d, is equal to omega times l times m1 L divided by m1 plus m2. Okay, so I cancel this, so this is essentially cancelling d from both sides. Now this gives me the expression for omega, which is v naught over L. Okay, so that's the angular velocity, and we have the expression for VCM. VCM turned out to be, let's see, the expression was m2 divided by m1 plus m2 v naught. And omega is v naught over L. So now we have a complete picture. As you see here, going back to this diagram, we have the expression for VCM, which is m2 divided by m1 plus m2 v naught, and we also have the expression for omega, so omega turns out to be v naught over L. So here, going back to this figure, then we can now say that the angular velocity that is produced, omega, is equal to v naught over L. Okay, now this gives us the complete picture, because we can now integrate this knowledge of the VCM and omega with this kind of a arbitrary configuration that we had sketched to show how the velocities of the individual masses are going to change in the ensuing motion. And remember that because there are no other external forces or torques acting on this system, then whatever angular velocity and VCM are produced at the instance when this impulse acts, that angular velocity and that VCM will remain unchanged. In fact, you can see that the angular velocity expression that we have also is a constant, because v naught comes from the magnitude of the impulse and L is the length of the string, the length of the inextensible string. So the angular velocity is also a constant. So which means that after the impulse acts on this system, in the ensuing motion, it's going to look like this. The center of mass will keep sliding with the velocity VCM in the x direction, while the two masses are going to start now rotating about the point C with an angular velocity of omega, which is v naught over L. And the overall mass of the individual masses, overall motion of the individual masses, is going to be a combination of these two effects: the linear impulse causing a linear velocity and the angular impulse causing a rotational velocity about the center of mass. So that's the overall motion, resulting motion of the system, and the thing that now needs to be found out is the tension in the string. Now, to find the tension in the string, we go back to how we have analyzed the system, and we understand that the translational motion, if there was only translation, so just for the sake of discussion, if this f hat, instead of acting at the mass m2, if it acted at the point C, the center of mass, it would have only produced VCM. It would have not produced the angular velocity. All right. But here the impulse is acting off center from the center of mass, or with an offset from the center of mass, and hence it is not only producing a linear impulse but also producing an angular impulse. Now, the linear impulse is producing a general fixed uniform motion across all particles in the horizontal direction. Okay, and when that happens, it does not cause the string to stretch. Okay, however, the fact that this is producing a rotational impulse, what that does is it creates a velocity, or it creates an additional velocity here and an additional velocity here. So it's creating a rotation about this point. And that is because the string cannot be stretched. And so what happens is that because the string cannot be stretched and it is producing a rotation motion, the rotation motion can only be sustained by tension in the spring, because otherwise you do not have a centripetal, you cannot produce centripetal acceleration. And a centripetal acceleration is absolutely necessary for any particle to have a rotational motion. So the tension is an outcome of the fact that there is an angular impulse. So the angular impulse produces a rotating effect which instantaneously produces the tension, and that tension maintains the rotation. Okay, so in order to find the tension, what we do is we say that because now M2 is rotating with respect to the center, so we can say that the tension in the string is, if you, for a uniform or for a rotation motion of a particle about a certain point, we know that the tension force is equal to the centripetal acceleration, and the centripetal acceleration is mv squared divided by L, or rho, where rho is the center of rotation. So M2 is rotating about the instantaneous about the center of mass C. So we have tension is equal to M2 times the omega squared d squared divided by d, mv squared divided by d. So let me just right, so this is the rotational rotational velocity, and this is the distance from the center of mass. So essentially you have m2, and omega squared is v naught squared over L squared, and then this d cancels one of the d's, and so you have d here, and the expression for d is, let me just double check, m1L divided by m1 plus m2. So the tension is then m1 m2 v naught squared divided by L times m1 plus m2. Okay, now you can also find the expression for tension by considering the rotation of m1 with respect to the center, and it's the same tension because the string is massless, inextensible. So the tension that shows up on m2 is the same tension that shows up on m1. So there is a tension force that is, so the tension force is like this, and it's the same tension force on both the particles. So then for m1 it is m1 times omega squared L minus d whole squared divided by L minus d, which is equal to m1 times v naught squared over L squared times L minus D, and L minus D is, we have found out L minus D to be M2L divided by M1 plus M2, so this is M2L. So I'm just showing the cancellation, and that is going to be again M1 M2 V0 squared divided by L times M1 plus M2, and we indeed get the same expression for the tension of the string, which is expected because the string is massless. So that is the center of mass based approach in resolving the motion of the particles, determining the translation, the rotation of the particles, and determining the tension in the string. There are some variants of this approach to solve this problem, which we will explore in our following videos, where we will continue this problem but try to take somewhat different approaches as we solve this, just to give a better idea of the different kinematics and kinetics that are involved in this problem.